Hi again, RetroAchievements enthusiasts. So if you've been wanting to make your own achievement set but felt too lazy to read through all the documentations on the website, we're gonna break it all down step by step in a way that actually makes sense. Our focus today is on the memory inspector. This is where you'll spend a lot of your time digging through RAM to track down variables used in games. Let's take a look at the new search tab in the memory inspector. Here you'll see a memory map that outlines the system and game memory. It's best to leave this as its default setting, as changing it usually won't impact your search results in a meaningful way. Besides that, you'll find another dropdown for choosing the memory value size. This can be a little confusing at first. As a junior developer, the most common options you use are 8-bit, 16-bit, 16-bit aligned, 32-bit aligned, and bit count, and sometimes float and ASCII, especially for later systems like the PS2 or GameCube. Okay, next, this drop-down menu stands for filter modes, and it represents symbols rather than terms. It goes like this: equal, less than and equal to, greater than and equal to, and finally, not equal to. The next drop-down menu represents search types. All of them are super useful, and I'll explain all of this later in this video. Understanding the difference between these sizes is crucial. Let's move to the memory viewer to have a closer look. Now, you're looking at a 32-bit view, but switch it to 8-bit reveals something odd, yet interesting. At first glance, the values does not seem to line up correctly. You see, these lines are flipped when switching between these value sizes back and forth. It's a little confusing, but when comparing the 8-bit view with 32-bit BE view, the lines lined up, but it's somewhat a mess compared to 32-bit view. And this has to do with a concept called endianness. In little endian systems, which most consoles use, the least significant byte is stored first. In big endian system like the GameCube, the most significant byte is stored first. Understanding this difference helps avoid misinterpreting data while scanning memory. The 32-bit big endian BE view was added later in the toolkit as a feature to support working with GameCube memory, since that system primarily uses big endian format. So if you ever plan to work on a GameCube title, you'll need to switch to the 32-bit BE view, because it's the most accurate and relevant way to interpret the memory. It's essentially the same as using a standard 32-bit view, just with the byte order reversed. I know it might feel like a lot to take in at first, but you'll end up spending much more time using the 32-bit view rather than the 8-bit one in most cases. Now let's break down memory size searches. For example, when you search in 8-bit mode, you're looking for values stored in single byte or 8-bit memory cells up to 2-digit values. This gives you a huge number of results, which can be a little overwhelming. If you're looking for a value like 5, say 5 lives, an 8-bit search might show you dozens or hundreds of results. However, using a 32-bit aligned search narrows things down by only looking at data in 4-byte chunk, producing fewer and more meaningful results. The aligned part means the memory is searched in neat 4-byte blocks. Important because searching without alignment can cause the result to span across boundaries, returning inaccurate or misleading data in the results. And the same logic applies to 16-bit versus 16-bit aligned searches. There's also a bit count option, which is especially useful when dealing with flags or bit masks, common in games that track unlockables or toggles. Bit count searches for values based on how many bits are set to 1 rather than the actual numeric value. For instance, if you unlock a concept art in a game, a single bit in an 8-bit value may change from 0 to 1. If all 8 bits are set to 1, which equals 0xFF, that means you've unlocked everything in that byte. Alright, let's dive into an example using Rayman 2: The Great Escape. In this case, we're trying to figure out how the game tracks the number of cages we can break in the game. It looks like this data is stored using bitflags. Now, make sure the bit count option is selected. We'll begin by starting a new search with the assumption that no cages have been broken yet. So the value now should be set to 0, right? Set the value type to constant and input 0 and click filter once. This filter's memory address is currently holding the value of 0. Next, go ahead and break a cage in-game. After that, return to the memory inspector, enter the value 1 since we've now broken one cage, and hit filter again. From here, click the continuous filter button. This will automatically filter out addresses where values are still changing, which is really helpful because we're trying to narrow it down to stable values that only change when cages are broken. Now, let's break a second cage. But before doing so, stop the continuous filter, because we're about to introduce a change and we don't want to filter out the very address we're trying to track. Once the second cage is broken, input 2 and press filter once. This filters for addresses that have changed from 1 to 2. Look closely at the results. You'll likely see a value where the bit representation now has 2 bits set. Couple of zeros, 11 and 0. Well, that 11 means 1 and 1. Those are the bits within the 8-bit value. That's bit 1 and bit 2 turned on, which lines up perfectly with us breaking 2 cages. This confirms that the value is stored as a bit flag. Each bit represents a different cage rather than a standard counter. Also, you'll notice that bit count now reads 2, showing 2 bits are set, meaning 2 cages have been broken. And here's something to keep in mind. The number displayed in the byte itself doesn't directly represent cages are broken unless you use bit count. For example, a value of 3 means bits 0 and 1 are set, not that it's literally 3 cages in a normal counting sense. That's why bit count is so useful. It lets you focus on how many flags or bits are active. Okay, now let's switch gears and see another example. This is my childhood game. Crash Bandicoot would be a good example for this part of the video. I'm in the first level where I can see only 2 indicators, Wumpa fruits and number of lives. So I'll open a new search, set the value size to 32-bit aligned, and set the filter to equal. If I currently have 4 lives, I'll input that value and click filter once. Now I'll collect a life pickup, that's 5. I'll hit filter once more, and there we go. If no matches come up, that means the value might not be stored as a 32-bit integer, so you'll need to lower the value size and try the search again. Keep in mind that searching with 8-bit values often returns more results. That's because the memory inspector will look for an 8-bit value at every single byte, 2-digit location, whereas 16-bit and 32-bit searches that has aligned flag to them will give less results, meaning they check every 4 or 8 digits respectively. Just be aware of the system architecture you're working with. The PS1 is a 32-bit system. Older consoles like the Sega Genesis and SNES are actually 16-bit. These older systems mostly store values in an 8-bit or 16-bit formats. In contrast, systems like the PS1, PS2, GameCube, or Nintendo DS tend to use the 32-bit values more frequently. Alright, now let's do the same thing for the Wumpa fruits. And there we go. I'll go ahead and add that to the bookmark window, and as you can see, it shows up right here. Speaking of bookmarks, let's look at the memory bookmark window for a second. The most important feature you may try often is to change how values are displayed, hexadecimal or decimal. This helps when cross-referencing in-game numbers with what's in memory. For example, this hex value, 0x14, equals 20 in decimal, so it represents the same value when you open the inventory. The maximum value of an 8-bit field is 0xFF, or 255 in decimal format. You can also search for the player's coordinates. Let me show you the trick quickly. So in 3D games, that usually means just X and Y positions, and they're often stored as 32-bit values. But since Crash Bandicoot is a 3D game, we're working with X, Y, and Z coordinates. So I'll start a new search by changing the value type to 32-bit aligned, and setting the filter mode to last value. Why 32-bit aligned? Because I think coordinate values are usually stored in 32-bit aligned. This is our assumption. So I'll hit filter once to get a fresh start, and slightly move the character to the right and switch the filter to greater than. We are just guessing at this point, but the idea is that if the X position increased, values that didn't increase will get filtered out. I'll click filter once again, then repeat the process. Move the character, filter, then move in the opposite direction and switch to less than, since we're expecting the value to decrease. Filter until the results get narrowed down. If there are still too many results, just switch to equal to last value and enable continuous filter. This filters out any values that change and keeps the ones that stay the same. I'll try jumping. I believe this won't affect the X value. Once I have a small list of addresses, I'll click bookmark selected to save them. Then I'll freeze all the bookmark addresses. To find the exact one, I'll unfreeze them one by one while moving the character until the character moves again. And there we go. That's our X position. Now, to find the Y and Z axis, they are usually stored next to each other. So when I jump and see a nearby address changing, that's likely the Z coordinate. And yes, this one reacts when I jump, so that's definitely the Z axis. These X, Y, and Z values are all 32-bit because they take up a full 4-byte chunk, which is more than 8-bit or 16-bit values can hold. So make sure to label this one as a 32-bit player X position, so you can easily identify it later. Another crucial variable to find is the level ID. This is super useful for triggering achievements when a player enters a specific level. To do this, you'll want to make a save state at each level. I've already done that to save time, so from there you can scan memory for values that change as you load into different stages, since those changes usually point to your level ID. This time we're not going to use the greater than or less than filter modes, because each level could represent entirely different values. For example, level 1 might use 0xF0, while level 2 might use 0x02. So filtering by value direction doesn't really make sense here. Instead, we'll use the not equal to last value to filter out things that doesn't change when loading into a new level. I'll start a new search, switch to another level using my save states, and change the filter mode to equal to initial value. Now keep in mind that initial value is what the memory inspector records when you first begin a fresh search. So basically, if we return to the same level we started in, we should see some values that resets to the actual initial value. That's what we're looking for. After filtering, I'll switch between levels and change the filter mode to not equal to last value. If this is still confusing, I have another good example later in this video. And we get a large list of results. Actually makes sense, because we're catching any value that changes. To narrow things down, we could skip the save states and just switch levels manually in-game. Now that we're back on the map, we expect the level ID to change again, so not equal to last value filter. Pick a different level, filter again, and keep going. So this process can be pretty tedious and time-consuming. But luckily it turns out that Crash Bandicoot, the level ID is actually really simple. Level 1 is stored as 0, level 2 as 1, level 3 as 2, and so on. This would have been hard to spot right away without knowing that in the first place, and not every game follows this pattern. Still, the approach I just showed you does really work. It just takes some patience to track things down. And usually the level ID is stored in static memory, meaning it often found early in memory. Now about those little buttons near the code note field, these are for saving and retrieving code notes from the RetroAchievements server. So if I click publish, I'll upload that node to the game's code note section. But this is important. If you're still a junior developer, it's against the rules if the game you're working on is not your own claim. So what I'm going to do instead is to delete the node from the server. The easiest way to do this is just simply empty the text box and hit publish again, and it'll get removed just like that. Let's have a look at another game of my favorites. In this level I can see a couple of crates lying around, and what I'm assuming now is that the game might be storing the total number of crates in a single address. I mean in a single byte. I'm guessing it's an 8-bit value, but since this is a PS2 game, I'm just gonna go ahead and search using 32-bit align to avoid ending up with a bunch of unnecessary results. Alright, I'm gonna start a new search and then change the filter type from last value to initial value. Now you might be wondering why initial value again? Why not just searching with last value like I used on Crash Bandicoot? Well, because PS2 games tend to have super dynamic and volatile memory. If I just keep filtering with last value, it's only comparing against whatever the previous value was during the last scan. That's not what I want. What I actually do want is to compare everything to the value that was there when I hit new search. That's the initial value, of course. This helps cut out all the random junk that keeps changing in the background and isn't related to what I'm actually looking for. So yeah, if I just hit new search and hover over a random address, you'll see there's a current value, last scan value, and initial value. From here on out, we're mostly comparing to initial value. Alright, let's start fresh. Set it to initial value and hit filter once. Now I'm gonna break a crate. Then I'll switch the filter to last value minus. We gotta type 1 in the box search field and hit filter once again. Perfect, so what does this 1 mean? What does this last value minus mean anyway? It means we broke one crate and we're filtering for addresses where the value went down by 1. Basically, we're assuming the crate count decreased by exactly 1. Now you might ask, why not just use constant and type the actual number like we did with warm-up fruits in Crash Bandicoot? Well, in this case, we don't know the total number of crates in the level. We only know that it decreases. It decreases by 1 when we destroy a crate. So this method works better. Okay, I'm just gonna go ahead and break 2 more crates. Okay, since the last scan, that's 2 crates total destroyed, not 3. So we type 2 this time and hit filter once. Nice. Now our address list is even smaller, but you'll still see some addresses flickering, right? They're just bouncing around constantly. That usually means they are unreliable or not what we want. We can easily exclude them by using the continuous filter. That will automatically filter out everything that's still changing. You can move around, do some stuff, just to be able to help reducing those annoying addresses. We're only keeping values that have stabilized, and now the results are looking even better. Let's shrink the list even more. I'm gonna go ahead and load a save state from before, the one all the crates are back together and unbroken. Now we got 2 options here. We can switch back to initial value and hit filter once again, or you can go back in the scan history using the arrows. Yep, this thing remembers like 50 steps and filter from there. Let's go with history. Go back 1 step. Now we know that we broke 3 crates before loading that state. So the crate count should have increased by 3, right? Now we set the filter to last value plus. Type 3 and hit filter once. And there it is. These addresses are tracking the number of crates in the level. They are 8-bit values, so I'm gonna select all of them and hit bookmark. I'll switch the display format from hex to decimal, so we can actually see the total crate count in normal numbers. And yeah, turns out the number is 30. I actually figured that out. You'd never figure that out manually unless you walked around and counted every crate. And even then, the 1 crate off and you're lost. Alright, let's talk about float, or floating point values. These are usually used for stuff that needs decimals or continuous ranges. Think health, coordinates, progress bars, timers, anything that's not a clean whole number. It gives you that extreme precision, even if it looks kind of messy in memory. Let's dive into that with a real example. I'm gonna try to ram dig the player's health. Now, I already know that in this game, the player's health is stored as a float. So I'll go ahead and start a new search and pick float as the value type. Okay, great. Now I'm gonna make the player lose some health. And since we just took some damage, I'm gonna set the filter to less than last value and hit filter once. Alright, we'll do that again. Take more damage, filter again to narrow things down a bit more. Now at this point we should switch the filter type from initial value to last value. Why? Because we are comparing changes from the last scan, not from the original, since we hit the new search. It just makes more sense at this point. Hit filter once again. Okay, now we're getting closer, but yeah. Switch the filter to equal to last value and then hit continuous filter. Boom, now we're cutting out anything that's still flickering or changing. We're only keeping values that have stabilized after we took damage. Now it's time to restore our health. I'm just gonna grab some health tags, whatever's in this level, to get back to full. Make sure to turn off continuous filter before doing that, because we're about to change our value again. Now, let's compare the changes we've done so far with initial value. You could load a save state, but honestly, doing it all in the same session is cleaner. If you load a save state, yeah, it resets the values, but it resets everything. Here we're only changing health, not all the background stuff. Once the player's health is fully restored, now we switch the filter type to equal to initial value and hit filter once. And there it is. After poking around a little, you'll probably notice of those addresses holding a not so weird looking float. In this case 500.0. That looks like our health. Let's bookmark it so we can mess around with it later. Actually, I'm gonna bookmark it twice, so you can see how it behaves in two different formats. One in floating point and the other in a 32-bit integer. Float is technically stored in 32-bit chunk, so both values are valid, just formatted differently. Now, if I switch one of them to float, we'll see it says 500.0. Makes perfect sense. But if I leave the other one as 32-bit, you'll see this kind of weird looking number. It might say something like 0x43fa, couple of crap, or whatever. This number looks weird, but it's actually normal for a float stored in memory. If you see values that start with something like 3f, 40, 41 up to 44, yeah, that's just the way floats look under the hood. Totally fine. And if you want to test it, go ahead and freeze the value or change it manually. You should see the player's health react in real time. You can freeze it and do whatever you want with it. That's full god mode. And yeah, that's pretty much how you use the memory inspector to dig for anything that comes to mind. Cheers and have a good one.